Hello and welcome to the solutions video for the Physics Unit 2 practice test. Just a bit of a heads up before we really get started. It looks like the normal whiteboard at Limnu is currently down due to an error on their side. So I'll be using a different whiteboard, which unfortunately I'm unable to share as easily. Right, so numeric response number 1. A slingshot accelerates a small rock at a speed of 80.5 meters per second from rest over the 60.9 centimeters it travels before leaving the slingshot. Assuming constant acceleration, the time it takes the rock to accelerate to this speed is a dot bc times 10 to the negative d. The values of a, b, c, and d are. We will go to our whiteboard. So our final speed is 80.5 meters per second. And it takes 0.609 meters to reach that point. Now we are asked for the time it takes to do this. So we have our displacement, we have our final velocity. Our initial velocity would be 0 meters per second. And sorry, we're asked for the time. The time is our unknown. So that means the acceleration is the one that's irrelevant. Oh. I've got to remember now how to actually scroll the canvas in this tool. Okay. That's a zoom. Select tool. There we go. Unfortunately, this whiteboard is really designed for a tablet. So the equation that is of use to us is VI plus VF over 2 times t. To find our time then, that's 2d over VI plus VF. Right? This is the equation which does not involve acceleration. So our time is 2 times 80.5 meters per second over 0 meters per second. Oh, that's not our time. Sorry, that's not our displacement. The displacement is 0.609 meters. So this is the calculation that we need to do. And I don't understand why the whiteboard is not being screen captured. Okay. I'm sorry, guys. I don't see it in the screen capture, in spite of the fact that there's only one whiteboard window available. And on my end, it is plainly visible. All right, this is interesting and frustrating at the same time. All right, I have no idea why it's not doing that. So let me maximize it. And if I switch from the whiteboard window to a display capture, that is working. Okay. So we've collected our information. Acceleration is irrelevant. And we do our substitutions. All right. So now we can go back to the assessment. We'll pull up a calculator with the calculator emulator here. We'll do the calculations. Our numerator is 2 times 0.609, and our denominator is 0 plus 80.5. So there we go, 0.152 or 1513. So this would be 151 times, or 1.51 times 10 to the negative 2. So 1512 in this notation. All right, in this one, the model of a rocket as it leaves a launch pad can be modeled as uniform acceleration. Students use an onboard GPS unit to measure the motion of one rocket. So it reaches an altitude of 128 meters in a time of 1.82 seconds from launch. Its speed when it reaches that altitude will be. All right. So this one, it can be modeled as a uniform acceleration. We do not know what acceleration that is. So for that, we're going to use the same equation that we were using previously. Oh, maybe that's the issue. The whiteboard window seems huge. Is it only capturing the top corner? No, that's not it either. Okay, we'll go back to the full display capture. We will be using the same equation. Oh, I was trying to change colors, but this is some kind of rainbow deal that is not necessarily easy to read. Oh, delightful. Do I have other? Ah, that's how we do the other colors in this one. Sorry that you guys are seeing all the growing pains as I'm trying out this other whiteboard. Okay, so VI plus VF over 2 times T. So we know our displacement is 128 meters. Our time is 1.82 seconds. And our VI, because we're coming from launch, will be 0. So we need to solve for VF. VF will be 2D over T minus VI. So 2 times 128 meters over 1.82 seconds minus 0 meters per second. So this is really 2 times 128 divided by 1.82. So 2 times 128 divided by 1.82, and we get 140.6593407 to 3 significant digits. That's just 141. And when the engines of the rocket stop burning, the rocket has a speed of 247 meters per second. Ignoring air drag, the rocket would be expected to travel how many kilometers further in the vertical direction before it comes to maximum height? So this is one without the rockets and ignoring air drag, the only acceleration is the acceleration due to gravity. And this one, we don't know, nor do we need to know, how much time has elapsed. So in this one, changing colors again, as we separate the questions. Without time, we have VF squared equals VI squared plus 2AD. Now our initial velocity, our initial velocity is 247 meters per second, but we are trying to solve for distance. So we're going to have VF squared minus VI squared over 2A. That's our distance of the displacement. Our final velocity is going to be when it reaches its maximum height, so that's at 0. The initial velocity is 247 meters per second, and our acceleration due to gravity is 9.81 meters per second squared. So it's really a negative of 247 squared divided by 2 times negative 9.81. So we can recognize it's going to be negative over negative and drop both negatives and just leave it as 247 squared, and then 2 times 9.81 is 19.62. So that's 3,109.531091 meters further. They're asking for kilometers. So this should be 3110, which is not exactly ideal for significant digits, but I know that's the way it's keyed simply because at no time has it actually suggested that we do this with scientific notation. Oh, no, you know what? That's in meters. It was asked for kilometers. I had to do the decimals, and that does bring it down to the 3 significant digits. So that takes care of that one. Number 4. In 2016, a group of hobbyists launched Sea Charger, an autonomous boat they had designed and built to travel without human interaction from California to Hawaii. Sea Charger traveled at an average speed relative to the water of 1.09 meters per second and took 41.4 days to complete the trip. The Sea Charger made the trip, it had to contend with ocean currents that would push it off course. In one stretch of the trip, Sea Charger encountered a water current with a velocity of 0.300 meters per second to the south relative to the shore. Okay. So in order to continue traveling directly west relative to the shore, Sea Charger would need to point in an angle of how many degrees north of west during this portion of the trip. So this one has a slightly tricky setup. Ooh, that is not what I wanted to do. There we go. So, our Sea Charger experiences a south or a southerly. Let's see if I can hold shift to make that straight. There we go. So the Sea Charger is going south. It wants to go west. So that means in order to combat that, we have to aim at some angle in this direction so that when we add them, our resultant vector is this one. So we're taking this southerly vector and this angled vector to add up to a purely westerly vector. Now, the important thing here, it travels at an average speed of 1.09 meters per second, and it encounters a water current with a velocity of 0.300. So we've got 0, oh, hang on, no longer need the arrow tip. So we have 0.300 meters per second this way, and 1.09 meters per second this way. And we are specifically asked for the how many degrees north of west. So they're asking for this angle theta here. So in that case, it's best to use sine, because our opposite will be the 0.300 and our hypotenuse will be 1.09. Sorry, so much flipping. Okay. So we want to do the inverse sine, or the A sine, 0.300 divided by 1.09. And that number, right, I see up here, we are in radian mode. And does it take pi? No, it doesn't. I have to find the pi button here. All right, so it's at about 15.97 degrees, or 16.023 significant digits. Sam and Chad are participating in a relay race. Chad is stationary when Sam runs past him at a constant speed of 6.9 meters per second. Chad begins running just as Sam passes him. Didn't say they were good at it, only that they are participating, and accelerates at a constant rate of 1.4 meters per second squared. How far will Chad have run when he catches up to Sam? So Sam has a constant speed. So Sam is moving at a constant 6.9, and Chad has to catch up, which means they have to travel the same distance in the end. So we have one of them running in a straight line at a constant speed, and the other one is speeding up to catch up. Eventually they do the same distance. So the distance that is it Sam or Chad? So Sam is moving at a constant 6.9. So there's going to be the distance that Sam runs is equal to the distance Chad runs. That's Sam's velocity times time, whereas the distance Chad runs is going to be Chad's initial velocity times time plus 1/2 Chad's acceleration times time squared. But his initial velocity is 0. So we can cancel that term. So it's v Sam times time and 1/2 Chad's acceleration times time squared. We can cancel one of the times. So time is 2 times the velocity of Sam over the acceleration of Chad. So it's 2 times 6.9 meters per second over 1.4 meters per second squared. So, going back to the calculator, 2 times 6.9 divided by 1.4 gives us 9.85714. Oh, hang on. That's the time. We need the actual distance. So we have to take that time, and it's easiest to find it by multiplying that by Sam's speed, 6.9 meters per second, and that's 68 meters. So that value for the time was there to trap us. Landing probes on Mars is made more difficult by the fact that the atmosphere is extremely thin. Okay. So if it's moving at 220 kilometers an hour and it drops the probe from a height of 150 meters, we have to turn that 150 meters into the amount of time that it takes this to fall. I'm going to try doing the full display capture instead of flipping back and forth. I'm just going to maximize both windows and flip-flop that way. So how long does it take to drop 150 meters? That's our first question. So we have the d is VIT plus 1/2 AT squared. That is 0. And let me come back here. All right, and the test of the airbags on Earth. So we don't need to worry about the acceleration on Mars. So 2d over a and the square root of that is our time. So we have 2 times 100, or the square root of 2 times 150. So yes, this is 2 times our distance is 150 meters. Our acceleration is 9.81 meters per second squared. Technically, our displacement and our acceleration should both be negative, but this gives us our time elapsed. We want to know how far it goes in meters. Well, 220 kilometers per hour divided by 3.6 gives us meters per second. So that's how many meters per second we're going. We multiply by the number of seconds we have, and it goes 338 meters. All right. A motorcycle travels 80 meters north in 15 seconds. It then turns around and travels 60 meters south in 10 seconds. So it travels a total distance of 140 meters. Distance is not a vector, it is a scalar. We ignore directions. So there'll be no north or south after it, it's just 140 meters. The displacement, it went 80 north, back 60 south, that's going to end up with a difference of 20 meters north. The average velocity is our displacement over time. 20 meters north divided by 25 is 0.8 meters per second north. Now, a soccer ball is kicked from the ground with a speed of 12.0 meters per second and an angle of 40 degrees. It returns to the ground in a time of 1.57 seconds. The distance traveled by the ball before it hits the ground. Here we're just looking at the horizontal distance. We don't need the arc length. So 12 meters times the cosine of 40 degrees, but our calculator here is in radian mode. So I'll just do a manual conversion because I don't remember how to change mode on this emulated calculator. So there is our velocity. And it takes 1.57 seconds to travel at that speed. So that is a 14.4 meters. And the maximum height reached by the ball. So we have a few ways to do that. Okay, we know that it's going to take half that time going up and half the time coming back down. So what's going to be the easiest way? All right. So if we, to find that height, if we do it with VFT minus 1/2 AT squared, looking only at the second half. So it's gone up and back down again. Oh, actually, no, this would be we'd want it as the VI plus, or VF if we look at the first half. We could do VI plus. Either way, we're looking for where the initial is 0. So the second half, we start with VI plus. If we look at the first half, it's VF minus. Either way, that goes to 0. So our total displacement is 1/2 times negative 9.81 meters per second squared times half the total time it spends in the air. So that is 0.5 times 9.81 times 1.57 over 2. And we square that, so 3.02. They've got 3.03, but that could be round off error from taking a slightly different approach. Maybe they even just used 9.8 for acceleration due to gravity. Vectors. Which are vectors of these 7? Car traveling north at a given speed, we know is a vector. The time something takes to hit the ground, time is not a vector. The length of a driveway, don't know the direction. Student travels westbound for a given distance, that's a displacement. We have a magnitude of the 80 newtons pushing down, magnitude and direction. And the last one, gravity here, in this statement, we don't see a direction, but the 80 kilogram man has one. So, car A is traveling at a velocity of 100 kilometers per hour north. Car B on the same highway is traveling at 110 kilometers per hour in the same direction as car A. So the velocity of car B, as seen from car A, go in the same direction, it's just 10 kilometers an hour faster. So that's 10 kilometers an hour north. So the north component for a car traveling at 21 meters per second, that's 16 degrees north of east. North of east happens to be the same as our standard position. So this will be 21 times the sine of 16 degrees. And again, don't recall how to flip this into degree mode. So that's about 5.79, or to 2 sig digs 5.8. Now the velocity vector of a cheetah is illustrated below. Moves at a speed of 18 meters per second. Which row shows the cheetah's velocity correctly as a magnitude and direction in component form? Well, here we need a positive x and a negative y, and y has a greater magnitude than x. So they've all got the signs right. Our y has to be the negative 16. So it's either B or D. 25 degrees. So that's east of south. So we're starting with the south and move 25 degrees east. It's less than halfway. So without touching the calculator, this is the way it goes. Now, just to be sure, before we finish our recording, I will check. Yes, there we go. So you now get a little sneak peek into what I'm going to do before I close each of these. And yeah, we have a 15 out of 15. So these are the solutions to our practice test.